You know, our digital world feels so smooth, doesn't it? We send a photo, stream a movie, and it just works. But behind all that magic, there's a constant, invisible war being waged against total chaos. Every single second, bits of data are getting scrambled. So what's stopping our entire digital lives from turning into a garbled mess? Well, the answer is some surprisingly simple and really clever math.
Just look at this. I couldn't believe that I could actually understand what I was reading. Your brain is an incredible error-correcting machine, right? It can look at this jumbled mess and, almost instantly, figure out exactly what it means. But a computer just sees garbage.
So how do we make sure that the emails, the photos, the vital files we send from one place to another arrive exactly as they were sent? Turns out, it all comes down to some beautiful, simple math that's constantly running in the background.
Okay, first, we need to get one thing straight. Data getting corrupted isn't some rare, freak accident. It's a constant threat. Every single time information flies across a wire or through the air, there's a chance it can get warped, lose a few pieces, or even pick up some extra bits it's not supposed to have.
And this isn't because your computer is clumsy or anything. It's really just a physics problem. You've got things like electrical noise from other gadgets, little hiccups in how data is routed across the internet, or even timing errors that are so tiny they're almost unimaginable. But any one of them can flip a digital 0 into a 1, or a 1 into a 0. And that's why checking for errors is one of the most fundamental jobs in all of technology.
So, how do you catch these sneaky little errors? Well, the very first line of defense is an idea that's so elegant and simple, it's brilliant. It's called a parity check. Let's just think of it as a little counting game.
The basic idea is this. Before the sender zaps a byte of data, that's just a string of 8 zeros and 1s. The sender and the receiver make a little agreement. They decide, are we going to play with even parity rules or odd parity rules? And based on that rule, they tack on one extra bit, the parity bit, to the end of the byte.
Let's see how this works if we agree on even parity. The rule is simple. The total number of ones in the message must be an even number. So, if we look at this byte of data, let's count them up. We've got 4 ones. That's already an even number. So to keep the total even, the parity bit we add is just a 0. The rule is satisfied. Perfect.
But what if we'd agreed on odd parity? Okay, we're starting with the same 4 ones, but now we need the total number of ones to be odd. So to make that happen, we set the parity bit to 1. Now the total count of ones is 5. When the receiver gets this message, it does a quick count. If the total isn't odd, it immediately throws up a red flag and says, nope, something's wrong here.
This seems pretty foolproof for catching a single mistake, right? But here's the twist. What happens if the universe decides to be a little extra tricky and flips 2 bits instead of just 1?
And here it is, the fatal flaw. Imagine not 1, but 2 bits get flipped around during the journey. A 1 becomes a 0, and a 0 becomes a 1, just like you see on the right. Now, if we're playing by even parity rules, let's count the ones. We still get 4. It's an even number, so the parity check is completely fooled. It gives the corrupted data a thumbs up, and the bad data slips right through. A simple parity check just can't catch every kind of mistake.
So, clearly we need something a little more clever. We need a way not just to know that an error happened, but to figure out exactly where it happened.
So how do we find the culprit? Well, we turn the data into a grid. Think of it like a game of Battleship. As you can see here, we don't just put a parity check on the rows of data. We also add one for every single column. Now, if a single bit flips, it's going to cause an error in its row and in its column. The computer just has to find the row that failed and the column that failed, see where they cross, and bingo, it's a hit. It has found the exact location of the faulty bit.
Building on that idea, we get to something called a checksum. This is even more powerful. Basically, an algorithm takes a whole chunk of data, does some fancy math on it, and spits out a single value, the checksum. You can think of it like a unique digital fingerprint. If even one tiny bit changes in that original data, the new fingerprint won't match the old one. The system knows immediately that something's gone wrong.
Now, this all might seem really abstract, like it's buried deep inside a computer chip somewhere. But you actually interact with a brilliant form of error detection every single day. Go ahead and pick up any book. You see that ISBN barcode on the back?
that's not just a random string of numbers. It has a secret mathematical code built right into it, designed specifically to make sure the number is scanned or typed in correctly.
And that secret is called a check digit. It's that very last number in the code. It's not random at all. It's calculated from every single digit that comes before it. Its entire job is to catch common human mistakes, like typing one wrong number or accidentally swapping two numbers that are next to each other.
So how is that last digit calculated?
For a modern ISBN, it follows a simple recipe. First, you add up all the digits in the odd positions, the first, third, fifth, and so on. Then, you add up the digits in the even positions and multiply that total by 3. You add those two results together. Now for the clever part. You divide that big total by 10 and see what the remainder is. Finally, you subtract that remainder from 10, and that's your check digit. Let's actually see it in action.
Here we go. This is the math for a real ISBN. When you run those first 12 digits through that whole process, it leads you to one single unavoidable answer. The final number has to be a 9. That's the check digit. So if a cashier scans this barcode and the system sees anything other than a 9 at the end, it instantly rejects it. Error. It's a beautifully simple piece of math that prevents countless mistakes every single day.
Okay, so we've established that our computers are fantastic at detecting errors. They can see a single flipped bit from a mile away. But what do they actually do about it?
Well, they use a system called an automatic repeat request, or ARQ. And honestly, it's pretty much exactly what it sounds like. It's the digital version of someone saying, "Sorry, I didn't quite catch that. Could you say it again?" This all happens through a constant little digital handshake. When a chunk of data arrives perfectly, the receiver sends back a little OK signal. If it arrives with an error, the receiver sends back a negative signal, which is just code for "please send that again." And what if the data just gets lost in cyberspace and never shows up? There's a simple timer. If the sender doesn't get that OK signal after a moment, it just assumes the packet is lost and automatically sends a fresh one.
So, from a simple counting game to the barcode on your bookshelf, these error checks are really the unsung heroes of our digital age. They are working away completely invisibly trillions of times a day just to keep our entire world from falling apart into a mess of jumbled information. It really makes you wonder, doesn't it? What other invisible math is out there, quietly and brilliantly running the world all around us?